Welcome back, everybody. This is our last chapter to cover in Stat 2000. We are almost there, just a few short sections left. So chapter 3, we are looking at the relationship between two quantitative variables. You may have noticed that I'm starting chapter 3 notes with section 3.2 instead of 3.1. The reason for that is the book organizes their content a little bit differently than we do in our course. And 3.2 we actually covered in a previous chapter. There was like two-way tables looking at categorical data in two-way tables. So we already covered that. So we're going to go ahead and get started with 3.2. 3.2 is pretty short. We're going to be looking at describing the relationship between two quantitative variables. So just a couple of things to mention here. You might be familiar with scatter plot. So this graph right here is called a scatter plot. A scatter plot is used specifically to look at the relationship between two quantitative variables. So way back in chapter 2, we looked at all these different graphical displays, pie charts, bar graphs, histograms, dot plots, all of that sort of thing. That was looking at one categorical or one quantitative variable. Here we're looking at two quantitative variables. So remember, a quantitative variable is a variable that takes a numerical value for which it makes sense to take an average. So we're going to see along our horizontal axis a quantitative variable, as well as our vertical axis will also see a different quantitative variable, and we can analyze the relationship between those two things by looking at trends in the data. So this first example, we're looking at the relationship between age in years and price in thousands of dollars for a random sample of used Honda Civic. So just to mention a couple of things about this scatter plot here. So we have the graphical display of the data, but notice we don't have a list of each of those individual values, and oftentimes you don't. So I mean, I can't even tell just by guessing how many dots are here, maybe 50, probably more than that actually. But notice we don't have a list of the actual data, meaning I don't exactly know what this point is. Like, I know the x value is 8, but I'm not exactly sure what the y value is or what the price of that vehicle is. So kind of keep that in mind as you're looking at new data here and looking at a new graphical display, that you may or may not know exactly what those values are. So that's important to keep in the back of your head. Also, when we're looking at the relationship between two variables, we want to think about one as the explanatory variable and one as the response variable. So we talked about the difference between those two things quite some time ago. It's pretty easy to remember on a scatter plot. The explanatory variable is usually written on the x-axis. So explanatory variable, x-axis, and then the response variable is usually displayed on the vertical or the y-axis. So in this case, we would think that the age of the car helps explain the price of the car. That makes sense there. So here, when we are describing the relationship between two quantitative variables, we want to think about 4 things. So those 4 things are here in bullet form: direction, form, strength, and outliers. So direction, we just want to look at this overall trend and ask ourselves, is there an overall positive trend or a negative trend? So we read graphs from left to right generally. So we want to think about from left to right, what is the overall trend? So from left to right, it looks like our trend is going down. So we want to think about above average values of age tend to correspond with below average values of price and vice versa. So we can also think about that as age increases, the price tends to decrease. Again, this relationship is for all of the points in this sample, so we don't want to think about, okay, if I randomly select 2 points, I should also see that trend. That's not necessarily the case, right? If I randomly select this point and this point, then that trend isn't there for just those 2 points. So this is the overall trend for this entire sample of data. Form, we're either talking about linear or nonlinear. In Later statistics courses, if you happen to take other statistics courses past this one, you might look more specifically at nonlinear data, and maybe you're looking for a quadratic relationship or an exponential relationship. But right now, for the purposes of our course, we just want to note, is the relationship linear or is the relationship nonlinear? So I did draw a few examples over here of nonlinear relationships. So this looks something like a quadratic, maybe this might look like an exponential, this one might look like a cubic function. We don't need to specify between any of those. We just need to know, let's identify the relationship as either linear or nonlinear. For strength, we're looking at how closely the explanatory variable and the response variable follow a linear relationship. So in short, how close are those points to a straight line? We are focused on linear relationships in this chapter. So that's why we're talking specifically about this correlation coefficient. So correlation coefficient describes the linear relationship between two quantitative variables. What that means is if we saw two quantitative variables that had this relationship here, it wouldn't be appropriate to use correlation coefficient to describe the strength of that relationship, nor would it be appropriate here or here. So correlation coefficient, we call that R, measures the strength of the linear relationship. Now that R does take a certain value. It's just a single number, but it does take into account every single point on that scatter plot or every single piece of data in that sample. So this may or may not be familiar to you, but R, our correlation coefficient, can take a value between -1 and +1. The closer the value is to -1 and +1, that means the data points fall in almost a perfect straight line if the closer they are to -1 or +1. If there is almost no linear relationship, then that correlation coefficient would be close to 0, and that would be a weak relationship. Another thing to note about correlation, the sign goes with the direction. So in our example here, we said that the direction was negative because we see that negative relationship here. Therefore, if we were to calculate our correlation coefficient, it would also be negative. So the sign of correlation does correspond to the direction, positive or negative. I did want to show you the formula. You will never have to calculate this on your own using this formula, but I wanted to show you this formula just to kind of talk about why this is actually true. So I'm going to use the formula to talk about why correlation is not resistant to outliers. So remember, resistant means if you have outliers, does that change the value of whatever I'm looking at? So we talked about resistant measures of center, mean and median a while ago. So now we want to know if I threw in an outlier in this scatter plot, would the correlation or the strength of the linear relationship change? And it would change. So therefore, correlation is not resistant to outliers. Now, the reason it would change, I wanted to show you this formula. So again, you would never have to calculate this on your own, but I want you to think about what this formula actually says. So we've got this 1 over n minus 1 part, we have the sum of, and then we've got these two things that we're multiplying together. Think about what this looks like. And think about what this looks like. Something minus the mean divided by the standard deviation. Something minus the mean divided by standard deviation. Where have we seen that before? If you said z-score, you're absolutely correct. So remember, this is two quantitative variables. So what this formula is saying is take the x value of every point and the y value of every point, find the z-score of each of those x and y values, multiply those z-scores together, and you're going to sum that for every single value, then divide by n minus 1. So the reason I wanted to talk about this formula is because think about an outlier here. An outlier in this case would be a point that falls outside the overall pattern. If that point falls outside the overall pattern, then likely the z-score for one of these, at least, is going to be really, really large. It's going to be far away. That point is going to be far away from the average. So I wanted to talk about it in those terms because the formula uses every single value in the sample. Then that gives us an idea that if we change one of these values or if we put in an outlier, then it's likely going to be very far away from the rest of the data. Therefore, this calculation is going to change. One other thing to note down here, numerical summaries supplement plots of the data, but they don't replace them. So if I just say R equals 0.9, we can't really make major conclusions about what the data looks like. We want to make sure that we have a good picture of the data. So a graphical display as well as a numerical summary will give us the most information about our data. So you wouldn't want to make any inferences just based on R or just based on a scatter plot or something like that. The next two are just examples practicing predicting what type of association there would be. So in number 2, there are 4 examples where I give you 2 quantitative variables in context, or 2 variables in context, and I want you to think about whether there's a positive relationship, a negative relationship, or no relationship. And then in number 3, I've given you 4 scatter plots with 4 correlation coefficients. So I would encourage you to take some time to go through each of those examples and make sure that you understand why each of these relationships are what they are up here, and that you can, match these correlation coefficients. So each of these is an R, so that you can match each of these correlation coefficients with the corresponding scatter plot.